Alrighty, howdy folks. So we are moving on to a new chapter, chapter 14. And this whole chapter is about functions of several variables. Did we already do functions of several variables in the previous chapter? The answer is no. And well, I don't expect you to remember all of the stuff that I said, but one of the things I mentioned is, back in calculus 2 and all that, let me put it this way. With the 2D stuff, what we had done was first studied things like y equals f of x, the graphs of y equals f of x, or x equals f of y. And for the longest time, until we got to calculus 2, we never knew what parametric curves are. And then we learned about parametric curves. And at that time, in the previous section when I was talking about parametric curves in 3 dimensions, I mentioned that in 3D, we actually study the parametric first and then talk about functions of the kind, the equivalent of y equals f of x would be z equals f of xy. So we will talk about them later. And here we are, and we are going to look at functions of several variables. Okay, definition. A function f of 2 variables is a rule that assigns to each ordered pair of real numbers x, y in a set D a unique real number denoted by f of x comma y. Okay, what? If you recall, the definition of a function back in 2D was a function f is a rule that assigns to every number x one and only one number f of x, right? It's a similar version here. So if you were to pick a point on the xy plane with some coordinates x and y, each of those points is mapped to some f of xy. For example, can I come up with a simple, ridiculously simple example? Yeah, f of xy equals x plus y. Would you agree that I have created a function of x and y? Yeah, because f of x comma y, x and y are the independent variables, and f depends on those values. And here we are, a specific relationship is f of x comma y is x plus y. We could have f of xy equals x square plus y square, or we could have f of xy equals sine of xy, right? We could have all those situations, and that's all this is trying to say. And the set D is the domain of f. In the sense domain, as before, what's the domain? Well, you say that a certain point xy is in the domain of this f. Please pay attention to this. We say a certain point x comma y, the ordered pair, is in the domain of f if we can actually find f of x comma y, or f of xy is defined at that point xy, right? For example, if I were to define f of xy as 1 over xy, is that function defined at 0, 0? No, because 1 over 0 times 0, which is undefined. So 0, 0 is not in the domain of 1 over xy. F of xy equals, f of x comma y equals 1 over xy. That point is not there. Would you agree that that concept is not any different from what we learned before? Yep. And what's the range? Well, if we take all the points xy in the domain, and for each one of those xy figure out the f of xy, and take a set of all those f of xy's, right? We would have a set of numbers, and those set of numbers is the range. As simple as that. Cool. All right, let's move on. If f is a function of two variables with domain D, then the graph of f, we can actually draw a graph of these things, is a set of all points x comma y comma z in R3. This R3 is a fancy way of saying it's three-dimensional, and we have three real axes, one real axis for x and y, and one for y and one for z. That's all it's trying to say. Such that, what is this z? Z is f of x comma y. Just as back in 2D, once we knew a function f, y equals f of x, we could plot the curve of x comma f of x. Would you agree? What is f of x? The y coordinate would be f of x. And for a specific x, we know f of x. That means for a specific x, we know the y value. Right? And so we plot all those points, x comma y, and we get a curve. Here, slightly different. We pick different values for x and y and figure out the corresponding z. So that's how we have a set of ordered triple x, y, and z. And we plot all those points. But interestingly, let me see if you can answer this. If we plotted x comma f of x, which is x comma y, what do we get? We get a curve. What would happen if we were to plot x comma y comma z? All this set of points, x, y, and z. What do we get? Do we get a curve? The answer is we actually get a surface. See, suppose the domain is these x, y, and x and y. Because I'm showing it in 3D, I just made it to be 0. Essentially, my whole idea is I'm picking different values of x and y. What's the z value? Let's just take it 0 to be 0. And for each of these xy's, I can figure out the corresponding f of xy, which is our z. So if we plot all those points, we actually get a surface. And that's the key. Now, what is interesting is, in the previous chapter, we continue to get a curve. We didn't get surfaces. Would you agree? Those parametric curves is what we call them. For instance, x of t, comma y of t, comma z of t. R of t is equal to that. When we plotted R of t, we got a space curve. But here, in this case, when we plot z equals f of xy, ladies and gentlemen, we actually get a surface. Cool. Next. These are awesome. Level curves. For z equals f of xy kind of surfaces, we must talk about these things called level curves. What in the world are they? The level curves of a function f of two variables, right? Two variables means x and y here, are the curves with equations f of xy equals k, where k is a constant in the range of f. So what we do is, to get level curves, I'll show this with plenty of examples. We set k to be different values. F of xy is equal to 1. F of xy equals 2, 3, 2.5. And each time when we do that, we actually get a curve. Does that make sense? would f of xy equal to some constant? Should that be a curve? The answer is yes. Think of it like this. Let's go back to that simple case of f of xy is equal to x plus y. Cool. If I say f of xy is equal to x plus y is equal to, say, 1, that means I'm saying x plus y equals 1. Is x plus y equal to 1 a curve? Yeah, it's that y equals 1 minus x. It's a line. Is a line a curve? Yeah, it is a curve, right? So f of xy, by setting it equal to a constant, we will get a curve. And by setting that k to be different values, we get different curves, right? And those curves are what are called level curves. Physically, what do they look like? What does it mean? Well, and here is a wonderful example. Check this out. In fact, I'll show you with GeoGebra a whole bunch of curves, the 3D surface and the level curves. Man, that's going to be quite fascinating. Here is the idea. Let's say this surface is our z equals f of xy. It's a hat-like surface. Okay. Now, for this hat-like surface, if we were to take a plane, if we were to take k to be a certain value, like here, x equals 20. K equals 20. What in the world does k equals 20 mean in this case? We are saying f of xy equals 20. For that, this is what we need to do. Can we draw a plane at a z value of 20? A flat plane at z equals 20. Yep, we can do that. Go parallel to the xy plane, draw another plane, but it better be at a height of z equals 20. Does that plane cut this surface? Yep, that plane cuts the surface. And when it does, what kind of a curve results? It is this curve. Cool. However, if we went to a height of 25, we get a different curve. We get a circle. Maybe it's actually an ellipse. I don't know about this particular one. This is a generic one. In fact, we'll go to specific ones pretty soon. So we get a circle or an ellipse of some kind at a different height. And at k equals 30, we get this. So each one is a level curve, right? The level curves of this function f of two variables x and y are all of these. Cool. Should I go to this directly? To sketch the functions of two variables, use yeah, maybe I'll just go directly to that. Originally, I did this for a function like square root of x minus 2 plus y minus square root of y minus 1. Yeah, check this out. So what do we have? I picked some weird one. 2 plus 3 times 1.3 raised to negative 3 over 1.1 times x minus 2, the quantity square, times blah, some blah, blah, blah. Basically, I didn't want to do a simple e to the negative x square times e to the negative y square. I wanted to shift it along the x-axis and the y-axis and also the z-axis. I wanted it to be elevated by 2 units, and that's why I added a 2. I think a simplest one could have been, z equals e to the negative x square times e to the negative y square. Okay. So this is the surface. z equals f of xy surface. All right, now check this out. How do we get these different level curves I said? Oh, you take a plane at different heights. In this case, I have this plane at a height of 2.25, and we let that plane intersect this surface. How would it look? When the plane intersects this surface, it would look like that, whatever that shape is. Can we see what that shape is? Yeah, why don't we look at it? Aha! It is actually a circle. Isn't that interesting? So, when the plane z equals f of xy intersects when our plane z equals 2.25 intersects our surface, we apparently get a circle of a certain size, of a certain diameter. Now, what else can we do? Well, I can show that curve over here. So basically at z equals 2.25, what that shape looks like, I have already shown to you that it's a circle. Now, why is it not drawing a full circle? I have no idea. Okay, with that, now let's do one thing. Let's change where the plane is. We had, right now our level curve is at z equals 2.25. Let me increase it to 2.5. So we go up a little, and again we get a circle, which happens to be concentric to our previous circle. Again, another concentric circle. So as we keep scooting up and up, as we let the plane go up and up, and each time take a section of the surface, I don't know, it's some kind of a weird, those gaps should not exist. It's just somehow something's going wrong with the rendering part of it. But as such, these are all full complete circles. So sorry about the display. And as you can see, as we keep going up, we keep getting concentric circles, in fact smaller and smaller. Cool? And these are all level curves. Each level curve is associated with a particular value of z, which, you know, in the previous one they called it as k, different k values. Okay, and what else can I talk about? Okay, this is something I wanted to mention. Is our surface a cone? If we were to do level curves of a cone, wouldn't we keep getting concentric circles just like this? So is our surface actually a cone? The truth is no. Our surface is not a cone. Can I show that to you? Let me see. Yeah. Does this look like a cone to you? It's not quite a cone. And how would these level curves look like? What would be the difference had this been in fact a cone? Any thoughts? Notice our increment of this a, which sets the height, is constant every time we are moving by 0.25. For a cone, what happens is, if we did that, each time we move by the same amount up and up, the circles will be not only concentric, but equidistant. They will all be at a same distance from each other. The one to the next one, the distance is the same as that to the third one. Come on, Sammy. the distance from the first curve to the second curve is the same as the one from second to the third curve and third to the fourth and so on. That's the point I'm trying to drive at. So this is not quite a cone. And in fact, this is a bell curve in three-dimensional bell curve surface. Why don't I call it a bell? Yeah, that's actually a bell shape. Yep, that's a bell-shaped curve. Okay. So that is one. And I think I have another example. Yeah, let me show this guy also. This surface, check this out. F of xy is negative 6y over x squared plus y squared plus 1. This is in the book as well. So that's why I picked it. What do? Same stuff. We'll take a plane at different heights, let it cut the surface and see what it looks like. Okay. So we'll start there and scoot it up. Whoa, that's a big thing like that. Are these concentric circles, would you say? It appears that they are all circles. All the level curves are circles. But would you call them as concentric circles? No, they are not. What do we mean by concentric? The circles have to have the same center. That's not what's happening, right? So these are not concentric circles. This is how it would look. And friends, let me tell you, this is the coolest thing next to sliced bread. When the time comes, I will tell you about, when we learn about what's called gradient, I'll talk about something called steepest descent and all that. But let me give you a quick heads up on that one. The beauty of these level curves is, imagine that this surface is actually the surface of a mountain. Okay? If we drop a drop of water on this mountain, or some water, which way would that water run down? Of course, because of gravity, it would run down. But the question is, in which direction? I don't know, man. Check this out. The level curves will tell you precisely how the water will roll. How? Let's say I drop a drop of water at this point. Can I say that? What does this correspond to? I don't know. I think this is at a lower height, right? Okay, let me put it this way. This curve is the present one at the highest, at the peak, sort of closer to the peak. So if I were to drop a particle of water here, that particle of water will go in a normal direction to that curve. What do I mean by that? We draw a tangent at that point and then draw a perpendicular line to that point. Whatever that direction is of that normal, this water droplet will go along that normal. Until what time? Until it reaches the next level curve. At this point, which direction does it go? Now we need to draw a new normal. When it reaches this curve, wherever it reached, we draw a tangent and a line perpendicular to the tangent, which is going to be normal. And the water changes its direction because, as you can see, is it so? Yeah. Dang, these are too close, so you cannot see it. Let's say trust me on that part, and let me show you more dramatically when the water particle does that, reaches someplace here. From here, it moved like that and just slightly changed, a little more change. But let's say the water particle was here. Now, normal to this would be more or less horizontal along this. But notice, normal here, with the tangent being that, is that way, right? Normal here was horizontal, but normal here to this curve is not horizontal. It's in fact at a certain angle. Physically, what does that mean? That means the water particle will change its direction and continue on like this until it hits this level curve. Where's the normal curve here? Oh, it's that way. So again changes its direction and again changes its direction. And understand that as it is moving from this curve to the outer curves, it is also flowing downward. So we are talking about, I don't know, say some point over here on the 2D. It's moving this way and then turns that way and turns this way and something like that. We can detect precisely the path that this would take. That's the beauty of level curves as a practical thing. Because I'm an engineer, I'm excited about crap like this. Okay. Guys, that's about it. I don't think there is anything else that I needed to cover in this section. So far as homework problems and things are concerned, I just want you to get onto GeoGebra and do precisely what I did here. Type in f of x comma y equals negative 6y over, x caret square, maybe put in parentheses x caret square plus y square plus 1, like that. Create a slider, create a plane, let the plane cut it, things like that. And play with different f of x, y's. In the book, they have given you many functions of x and y. Yeah, try to plot quite a few of them and study them. Cool. That's it, folks.